So in my first lecture, I explained the Lindenbaum-Tarski theorem, and I hope at least said that it cannot hold for intuitionistic type theory in its original formulation. And that is for the following reason. Tarski himself pointed out that the theorem fails. The original Lindenbaum-Tarski theorem fails as soon as your simple type theory contains individual constants or function constants for functions from individuals to individuals. As soon as the individual domain has more than one element, and that is clear, as soon as there are two distinct elements, then there are isomorphisms of the individual domain which don't hold them fixed. You can always switch them by means of an isomorphism. Intuitionistic type theory, unlike the simple theory of types that Lindenbaum and Tarski had, has of course lots of individual domains to begin with, but above all it has lots of elements of individual domains. For instance, the two-element domain is there, which has the two elements, whether you call them 0 or 1 or true and false. And they are not respected by, they are not kept invariant under isomorphisms. So the theorem itself has to be reformulated. And that's why I call it an analog of the Lindenbaum-Tarski theorem. And what this analog says is that every definable object in intuitionistic type theory is not isomorphism invariant, but relation invariant, and I will have to explain, of course, what that means. And it turns out that this notion of relation invariance is the same as the notion of extensionality. So clearly I have to explain what it means for an object of intuitionistic type theory to be relation invariant. What that means depends on the category of the object. As we saw in my first lecture, we have every object has a category, and there are many of these categories. And what it means for the object to be relation invariant depends on the category. And remember then what the categories were. They were the category of sets depending on variables x1 in A1, etc., xn in AN. Maybe this time I should write out the variable dependencies here. So AN here depends in general, as we know, on the previous variables. And then the other form of category was element of A depending on n variables. So I have to explain what it means for an object of this category to be relation invariant, and I have to explain what it means for an object of this category to be relation invariant. Let me begin with the case n equals 0. So I deal with the first of these cases when n is equal to 0. Then to say that A is relation invariant is nothing more than to say that A has been equipped with a relation, P, say, a relation between A and itself. So a relation which relates A to itself. And I think I will allow myself to write this when it is convenient simply as A, and I will use the isomorphism symbol here, but it doesn't mean isomorphism now any longer. It just means that we have a relation between A and itself. So this is what it means. So we read this as A is related to A, or A corresponds to A. So that's what it means for a set to be a relation invariant. And so this is the case when n is equal to 0, as I said. And in the case of the second form, when n is still equal to 0, what does it mean for an element of A to be relation invariant? Well, it means nothing more than that it's related to itself relative to the relation which A is equipped with. So we should have a proof P that little a here stands in the relation capital P to itself. And that I will allow myself to write again as simply A is related to itself. So we see that the relation invariant objects in both cases are those which are self-related or reflexive, if you prefer. And I will also allow myself to read it as being extensional, but that is not visible in the case n equals 0. So let me now turn to the case when n is greater than 0. Well, I've already displayed the form here, but I have unfortunately not displayed the variable dependencies there, so I will have to rewrite it. So what does it mean for capital A here, which now may depend on the variables x1 up to xn to be a relation invariant? Well, I think the most intuitive way at arriving at the correct definition is to first write down what it naturally means for this to be extensional, since relation invariance and extensionality will come to the same thing. And that is easily done provided we allow ourselves to work with this isomorphism symbol, although it doesn't mean isomorphism any longer. So it just means that A of x1 up to xn should be related to A of x1 prime, say, up to xn prime, provided x1 is related to x1 prime. And I guess we have x1 and x1 prime in A1, and x1 is related to x1 prime, and so on. Xn in an of x1 up to xn minus 1, and xn prime in an of x1 prime up to xn minus 1 prime, and finally xn related to xn prime. And now we decipher this further in view of what I have said here in the case n equals 0. This should mean that we have a relation between a of x of these arguments and a of these related arguments. So let's call that relation capital P. So there should be a relation capital P, which will depend on x1 and x1 prime, provided they are x1 prime, provided they are related, which is to say that we have a proof of this, little p1, say. And p1 should be a proof that x1 and x1 prime are related with respect to the relation that we have over a1. Let's call that p1. And so on until we come to the nth arguments. Then we will have no, sorry, I have written it wrongly here. So the typing, of course, we never write the typing here. Typing. So we have this, there should be a relation, capital P, between this set and that relation will depend on all these arguments, xn, xn prime, pn. So this will be a relation between a of x1 up to xn and a of x1 prime to xn prime in the context where x1 and x1 prime range over a1 and p1 proves that they are related. That's where I was a moment ago. And then finally we have xn here is in an of x1 up to xn minus 1. And xn prime is in an of x1 prime to xn prime. And finally, Pn here proves that they are related. And that is to say that Pn proves that the corresponding relation capital Pn that you have associated with an here should hold between xn and xn prime. So Pn, which then depends on x1, x1 prime p1, etc., xn minus 1, xn minus 1 prime p n minus 1. That relation should hold between xn and xn prime. So now we have the whole context here. So this family of sets capital A is relation invariant, provided it has been equipped with this relation capital P, which depends on these 3n arguments that we have here. So the context that you have beginning there and ending there is now length 3n rather than this context, which is of length n. So that's the definition of what relation invariance means for this category. And then we have to do the same here for this case. I hope to be able to do that downstairs here, I think. So now we will have a little a there depending on x1 up to xn, which is an element of a of x1 up to xn in the same context as before. And this is relation invariant if when we change the arguments to some other arguments, x1 prime up to xn prime, the two are related with respect to the relation that we have here. So that means that we should have a proof that they are related relative to this relation, and let's call that proof little p, say. So then that proof little p will depend on the same parameters as here, p of x1 and p1. And what that proof will prove is that a of x1 up to xn is related by this relation to the corresponding thing with primed arguments. So this should prove capital P of x1 prime p1 of a of x1 up to xn So that's the generalization of this to the case when n is greater than 0. And the context here is, of course, the same context as we have up here. So I can just write actually same context here. So I now define the notion of relation invariance, or if you prefer to call it extensionality, for the second form of category.
Excuse me.
Yeah.
How do you avoid Tarski's
Well, that will be yeah, maybe I could give a short answer immediately, although it will be clear when I come to the particular case of the Boolean values. But the short answer is that in Tarski's definition of isomorphism invariance, there was the universal quantification for overall R, overall isomorphisms R. And that universal quantification is dropped here. So I'm not saying that it's invariant under all relations. I'm saying that we have invariance with respect to a particular relation which each set comes equipped with. So now the definition of relation invariance or extensionality has been given, and it remains to prove this, to establish this. And so it says something about all definable objects, and an object is definable if it can be expressed by an expression in the language. And hence the proof of the theorem is naturally by recursion over the build-up or induction over the build-up of that expression. So the short way of saying what we have to do is to say that if this is definable, then we have to show that it is relation invariant, which is to say we have to equip it with an A star which establishes its relation invariance, and in this case that was simply a relation on A. And in the second case now, for no argument, no variables, so if we have this definable, then we have to provide a proof A star that little a is related to itself relative to this relation. Now this relation and this corresponding proof is of course really, it depends on the expression that defines A, capital A respectively little a. So what stands under the star here should really be thought of as that expression. So although this is a good enough way of expressing it for most purposes, if we are more pedantic, we should rather say that what goes on here is a model construction where we associate with each set expression of the language, we associate two things. On the one hand, the set that it expresses, let me call that a dagger, and on the other hand, this relation A star, which should be a relation on this set that A expresses. And in the second case, similarly, if A is a capital A expression, that is an expression of an element of A, then we associate really two things to it. One thing is the element expressed by A, and the other object is this proof A star that that element stands in the relation capital A star to itself. So writing it this way rather than in this shorter way, it's clear that there is a model construction going on here. Now we have the familiar pattern that with certain expressions in the language we associate certain objects, semantic objects. What is now visible is that it's two-dimensional in the terminology of Bob Harper and Dan Licata, because we are not only associating one object with each well-formed expression, but two objects. And if there were n objects that we associated, it would be n-dimensional. Now, what is the dagger here? Well, the dagger is just the what takes any well-formed expression into its intended interpretation. So the dagger is the standard model. Of course, we know all how that is defined. If we have the set expression capital N, say dagger of that is just n, and if we have 0, 0, the expression 0, 0 dagger is just 0. And if we have the expression S of A, its intended interpretation is the successor of the intended interpretation of A, etc., etc. It's those equations that define the intended interpretation or the standard model. Now that means that applying these rules finitely many times, we can prove for each specific set expression A that A dagger is equal to A, and similarly for an element expression that A dagger is equal to A. We have to run through the expression here using these equations to get this result. But this shouldn't be taken to mean that it holds uniformly, that is, that this is the definition of the intended interpretation. The definition is here in these equations, and these are consequences of the definitions, but doesn't hold uniformly. So it's exactly the same situation as with Tarski's material adequacy condition in his truth definition, that you don't have uniformity, it holds for every specific instance. So I think it's natural now, since this is the intended interpretation or the standard model, to describe this model as an enrichment of the standard model. That is, we enrich what we have here with something more. And we have to, when we go through the rules, we have to see to it that we can properly define this enrichment for each rule of the theory. So let's start to do this. And it's clear that because of the number of rules in type theory that it takes time to go through all rules, and I propose that we deal with the variables. They are, after all, some of the symbols that we start from. Deal with one basic type as simple as possible, the Booleans. Then we deal in detail with the most important case, perhaps, the pi operator, which is simultaneously the universal quantifier. And that will have to stretch into the last lecture. And then I should be able to say something at least about how a universe is treated. And that will have to be enough. There are the sigmas and lots of other inductive definitions and so on, but it's more than we can manage. So let's begin now with the variables. Now, so before I wipe that out, that means that we have now the task of finding this capital P, respectively the little p, for the various forms of expressions we have, which means that I can retain these formulas here and say that we have to find, corresponding to capital A here, we have to find the A star, which satisfies this, where P1 ranges over A1 star of x1, x1 prime, etc. And here, instead of Pn, we will have capital An star. And similarly, in this case, we will have A star, little a star here, which will prove capital A star of this. And then nothing to change here because I've cleverly written same context. So let's go to the variables now. What does the rule for variable introduction look like? So if we have a context gamma, and we have a set in the context gamma, so I should say that means that gamma is x1 in A1, etc. N, that's what the context is. Then we can infer that x in A in the context gamma extended with x in A. Now this context gamma in the interpretation is turned into the context that we have over here, which is this whole context beginning there to there, which, as I said, has length 3n. And let's call that context gamma star. This whole context is gamma star. So in the interpretation, we will have instead the context gamma star. And we will have the interpretation of this, which is written precisely here. So we will have I don't think I need to repeat it. It's sufficient that we have it here. And now we have to find out what is the interpretation of this. In particular, what is the interpretation of x here. So we have to find x star. What should it be? Well, X star should prove under all circumstances that A star, which depends on all these variables, x1, x1 prime, p1, etc., xn prime, pn, that holds, that relation holds between x and x prime. If you see, we are in this case, since it's an element we have here, and we have to substitute in here the corresponding primed element. And all of this should hold in the context now, which is the interpretation of this context. And what is that? Well, it's gamma star with the three new assumptions x in A of x1 up to xn, x prime in A of x1 prime up to xn prime, and finally the proof P that x and x prime are related, and that proof P is A star of all the arguments x1, x1 prime, p1 up to x prime, pn. And it should relate x and x prime. So now it's clear what the interpretation of x here must be, p simply, because p has the right type here. So that deals with the variable case. So now let's go on to the simplest possible ground type, namely the Booleans. I thought first of taking the natural numbers as the prime example of a ground type, but it's good that it's even simpler than the natural numbers. So what is it I have to do? We have the standard axiom that bool is a set. Oh, maybe I could write it up here. And I have to enrich this by the star of it, bool star. And what should bool star be? Well, it should be a relation between bool and itself. So I have to define this. Well, this already gives the typing of bool star. So I should simply label this bool star formation. So the pattern that will appear now from the few examples that I consider of the rules is the following, that to the standard rules, there will be, all the standard rules will be accompanied by the corresponding starred rules, which will be the interpretation of the standard rules in this new model. That means that we get a duplication. We get twice as many rules as we have in the original theory. So in particular now, we are in such a case, namely that we have the standard rule, which I just wiped out, of bool formation. And that will now be accompanied by the rule of bool star formation, which simply says that bool star is a relation on bool, or what amounts to the same is to say that if A is an element of bool and if A prime is an element of bool, then bool star of A and A prime is a set. Remember by Curry-Howard that set and prop for proposition means the same. So we can write it either this way or that way. And I'm using natural deduction notation now, so that there may always be assumptions that you don't see on top. So that means that the interpretation of the standard rule is gotten immediately from this new rule, whether you write it this way or that way. But this is just the formation rule for bool star. We have to explain what it means also, and that is, as always, done by the introduction rules for it. So we have the rule of bool star introduction. And what it says is that bool star is defined by saying that it's the relation which should hold between 0 and itself, and also between 1 and itself, if 0 and 1 are the two elements of bool. So we should have, that means that we should have a proof 0 star, which proves that 0 stands in the relation bool star to itself. And we should also have a proof 1 star, that 1 stands in the relation bool star to itself. And these are all the introduction rules. And you see that gives us immediately what we must have in order to interpret the standard rules for bool, namely that 0 is in bool and that 1 is in bool, because what we have to show precisely is that 0 is self-related, and it's 0 star that proves that, and that 1 is self-related, and that is proved by 1 star. So now we come to the elimination rule for bool star. And of course, that's a new, this is a new, bool star is a new construct, but the definition of it follows the same pattern as these standard rules. So it has its formation, introduction, elimination, and equality rules. And now the question is, what does the elimination rule look like? I'm afraid I have to take this away now. So bool star elimination. Well, since the introduction rules are here, the elimination rules are determined mechanically from the general pattern for inductive definitions that we have for type theory. It's just to follow that general pattern. And in this case, what does it mean? Well, if we have a family now of one more argument than bool star, which is to say 3 arguments, let's call them z, z prime, and r, where z and z prime are in bool, and r proves that they are related. And moreover, we have proofs D0 that this relation holds of 0, 0, and 0 star, and 1, 1, and 1 star. D1 say that D holds of 1, 1, and 1 star. Then we may define a function f, say, of z, z prime r with values in capital D of z, z prime r for z and z prime in bool and r in bool star of z and z prime by, so I'm now writing the elimination and equality rules in one go here. By putting f of, we have to put in the arguments as we get them from the introduction rules. So it's f of 0, 0, 0 star should be set equal to D0, which has type and similarly then for 1, 1, and 1 star. So with this, the rules for bool star are complete. I mean, formation, introduction, elimination, and equality. And these rules follow precisely the standard pattern, although, of course, they are different from the rules for bool itself. So now we have to see to it that with these new rules, we can validate the standard bool rules in the two-dimensional model. So I've already remarked in connection with the formation and the introduction rules that these rules are precisely what is needed to validate the bool formation and bool introduction rules in the model. So here I need to not to say anything new, but we have to consider the rules of bool elimination and bool equality in the model and see that they become validated. So what are the rules of bool elimination and equality, the standard rules? Well, it's simpler than this, of course. If we have just a family C of Z, where Z ranges over bool, and C holds, and we have a proof C0 that capital C holds of 0, and a proof C1 that capital C holds of 1. Then we may define a function f of z, say, with values in C of z by the equations f of 0 equal C0 and f of 1 equals C1 in C of 1. So these are the standard rules. Now, what happens to them in the model? This is what happens when we put a star on everything in these rules. Well, let's begin with this. So in order for C of z here to be relation invariant, it has to come equipped with a C star, which depends on z prime and this proof little r, which should relate C of z to C of z prime. And this for z prime in bool, and R proving that proving bool star of z prime. So this is how this comes out in the model. And what about this? Well, C0 star should prove that C0 is related to itself relative to the relation which interprets C of 0. So it should prove C of 0 star of C0 and C0. And here, this I will rewrite now immediately using a substitution property as C star. So this is a substitution here, and there is a general rule that you may rewrite such a substitution in the way I did just now. So this substitution rule, which I will not establish but take for granted, is the rule that if you have, say, capital B of A star, that's the same as B star of A, and A star on the set level, and on the element level, similarly, B of A, say, star is B star of A star. So if you're handling substitutions in the traditional way, this is, of course, something that must be established by induction over the buildup of capital B and little b. But the only way to do this in a completely satisfactory way is to have explicit substitutions, but that goes well beyond what I can say something about here. So this is how the second premise comes out in the model, and the third premise then similarly, of course. So that's for the premises, and now we come to the conclusion. What is it that we must try to get in the conclusion? Well, we must try to get an F star of the three arguments z, z prime, and r, proving that f of z and f of z prime stands in the relation that interprets this. So we should have c star of z, z prime, r of f of z and f of z prime. Again, in this context that we have here, so I need not repeat that. And finally, we should satisfy these two equations in the model. And when you apply the model star to them, you get the equations f of 0, 0, 0 star equal to C0 star, which is in C star of 0, 0, 0 star of C0 and C0.
Maybe that's F star of.
Thank you. And now I will rewrite this immediately by means of the equation C0 equals f of 0 as C star of 0, 0, 0 star of f of 0 and f of 0. And similarly in the 1 case, of course, just replacing 0 by 1. So we have to get these conclusions from the premises that we have here. And fortunately, we have some means for it, because we have these rules of Boole star elimination and Boole star equality. They don't say exactly this, but fortunately, they have them as a corollary. Namely, we apply the rule of Boole star elimination and equality with a particular choice of capital D. So we choose the D that we are free to choose there. D of z, z prime r. We choose it as C star of z, z prime r applied to f of z and f of z prime. So with that choice, what do we get for these two premises? No, I should say, we choose D in this way, and we choose D0 to be C0 star. Which we know is in capital C star of here. Of C0 and C0. But now note that C0 is f of 0. It's just the standard elimination rule for bool. So this is the same as C0 star of 0, 0 star of f of 0 and f of 0. And this, because of the definition that we have made here, is nothing but capital D of 0, 0, 0 star. So that means that we now have this premise. And similarly, of course, with the 0 replaced by 1. And that means that we can conclude by this rule that f can conclude that f of z prime r is in d of z prime r, but that was defined this way. So this is in c star of z prime r of f of z and f of z prime, satisfying these equations, which is to say f of 0, 0, 0 star equal to d0, but d0 was defined to be c0 star. Which is in C star. And similarly in the one case here. So let's compare now that with what we wanted. We wanted to derive this, and that's exactly what we have here, hopefully. And we wanted to satisfy these equations here, this one and the one corresponding one. And we can conclude this because this is equal to d of 0, 0, 0 star. So this finishes the bool case now, and finishes also the lecture. So what is important to keep in mind from this is the pattern. And that's a general case for type theoretical investigations, that usually it is the whole conceptual pattern that is the most important thing. But you cannot see a conceptual pattern in abstracto. You have to see the pattern realized in sufficiently many special cases in order to be able to see the general pattern. And the pattern that is now beginning to emerge here is this, that in this new model, which is an enrichment of the standard model, the validity of the standard axioms in the new model follows from certain rules for these new constructs that are marked with a star. These rules for the new constructs, they follow the same pattern as we are used to in type theory. I mean, they are actually instances of the general scheme of inductive definitions that was formulated by Christine Paulin and Thierry Coquin in the early 90s. So these new rules are in that sense not new. I mean, they are new compared to the Boole rules, but they are not new compared to this general scheme for inductive definitions. And it's these rules which give, these new rules which show the validity of the standard rules in the non-standard model, in the new model. And we'll see this pattern repeated in the pi case and hopefully the universe case in the last lecture. And then I want to finish the whole series by reproducing a proof by an observation by Thierry Coquin that this model, I mean the relation model, if you want to call it that, or the model of logical relations, if you are familiar with the term logical relations, that this model actually refutes the law of excluded middle. So the situation is the same as with the univalence axiom of Vojevodsky. It's also, and if we go back in time, the same as with the continuity principles that you have in the intuitionistic theory of spreads and choice sequences, that the law of excluded middle is actually refuted by the model. Thank you for today.
Per, so far, the relations that you've used have all been just the graphs of automorphisms that live in a subgroup of the entire automorphism group of the classical structure. Is that going to continue?
So you say that they are invariant under a subgroup of the full automorphism group. Yes, a very small subgroup in this case.
Yeah, well, I mean, even if you have integers, you could move it up and down. And
yes, but the question is if it's so small that it has not much more than one element. So the subgroup of the isomorphism group in this case will consist just of the identity in this case.
Let me better formulate my question. That is that the objection to the Tarski-Lindenbaum theorem in the constructed case is that you don't want to move constants. Well, if you could always take the subgroup of the automorphism group that fixes those elements. Are we forced to go beyond those graphs, those relations in this model?
You mean we have to leave the definable elements invariant, but not necessarily more, you say. So it's a question of how the isomorphisms are allowed to operate on possibly non-definable elements. No, I cannot say anything offhand
Maybe you'll tell me
on that. Probably not, because the simple examples won't do, because all elements are definable. So one would have to consider the pi case, first of all. And as you will see, just interpreting the pi rules correctly is a certain amount of work. And I doubt that I can have something intelligent to say in response to this on Friday.
I don't exactly have a question, but I have something to point to and see if you have any interesting thoughts on it. So in mathematics, there's this distinction between properties and structure, where a set can be inhabited or not, that's a property, but multiplication operation on that is additional structure. And that essentially has to do with the fact that there could be many possible operations, whereas there's only one, something either is inhabited or it's not. And so in this case, it sounds, when we say something definable is relation invariant, that sounds like a property, but really it's more like a structure, because we're adding a specific new relation on. And so I guess I just wanted to point to that and see if you had any thoughts maybe in connection with the two-dimensionality of the system.
No, you are completely right. I mean, this is just an attempt to state the theorem in such a way that it looks as familiar as possible, but and then it is stated in this as the satisfaction of a certain property here. But when that satisfaction of the property is spelled out constructively, what it means, then it's exactly as you say. It means that we have more structure around the whole time that we must carry around. So it's just a general fact of constructivism that we say that to know that some property is satisfied is to know a proof of the proposition in question, and then everything takes place by means of operations on those proofs. Yeah.
I'll allow myself a question. So the theorem that you're attributing to Lindenbaum and Tarski was actually proved by Rudolf Carnap in 1929. Mm-hmm. And Carnap formulated it a little bit more carefully. He said that every property of a certain kind is stable under all automorphisms of the domain. And he called the special properties formal, just to have a word for them. Mm-hmm. And he defined inductively and the issue was exactly the one you're pointing out. That if you have a name for some constants, well then of course, for example, being identical to that constant is not a formal property. And so he went through and first defined inductively what it means to be a formal property. And it's one that doesn't involve such constants. And then he proved that every formal property is invariant under all automorphisms. And then when Lindenbaum and Tarski did it, and they were, by the way, familiar with Carnap's
very familiar, yes,
work, and they cited a footnote to Carnap's unpublished manuscript in this paper. When they did it, they avoided this problem by looking at the pure type theory, where you don't have the natural numbers in there with constants for 0 and 1 and so on. You just have a domain of individuals and no constants.
Right.
And that's how they get away with not dealing with this problem. So that's one possible solution, and I think that you can do the same thing for intuitionistic type theory. If you just look at the domain of a general domain of individuals, automorphisms of that domain, and then consider such formal properties of individuals, one will get the same kind of an automorphism invariance property.
So if you extend the intuitionistic type theory with one new domain or set, which is left completely unspecified, then you might hope for isomorphism invariance with respect to isomorphisms of that domain. Right. That's not excluded.
Well, in fact, my next observation was that the consistency of the univalence axiom implies that such types must in fact be automorphism invariant. Because if it were not the case that any such arbitrary type defined over an arbitrary domain were automorphism invariant, and you could find such a type that's not automorphism invariant, that would contradict the univalence axiom. And since we know that the univalence axiom is consistent by Voevodsky's model, it's a kind of soundness property for such automorphism invariance.
Clever.
Yeah. But what you're going for is an even more general invariance result than just automorphism invariance. Your invariance has this property of for an arbitrary reflexive relation being invariant. Modulo Rick's remark that so far we're only looking at graphs of automorphisms, but I think your result will in fact in the end be more general than just graphs of automorphisms.
Yeah, I have a much more general notion of invariance.
Absolutely.
That's true. But this result of Carnap's from 29, you said, is it in print or?
It is now.
But
It wasn't at the time.
It wasn't at the time.
Right. I can give it to you.
Oh. So, I mean, it's exactly the time of his book, Aprister Logistik.
It was subsequent to the book. He was doing some investigations. He called them investigations in general axiomatics. And he published a brief abstract. He gave a talk about it at the famous Königsberg conference.
Yes.
And there's an abstract published in that same proceedings of that conference. And then the manuscript itself involved some difficulties, and he didn't publish it after conversations with Tarski about this same, related to this same issue.
And you think that the footnote in the Lindenbaum-Tarski paper is adequate?
No, absolutely not.
No, that's, that's exactly what it seems to me. So I have to make some changes, it seems.
Okay, we have a question from Peter Axel at the Institute. If we're ready for that, I'll turn the sound on. I'll try to do that. Let's see. Oh, we're on a delay.
Can you hear us?
Yes, I can hear you. So here's Peter Axel.
Can you hear me? Can you hear me?
Yes.
Yes.
We can hear you. We're on a delay.
My question may have been answered or in some way by Steve's comments. The theorem that's being proved is an analog of the Lindenbaum-Tarski theorem. Do you expect to get, as a corollary of your theorem, something like the Lindenbaum-Tarski theorem for type theory?
There was a crucial two crucial words that I could not hear, but I think I understood the question. So far, I have not expected to get a version of the Lindenbaum-Tarski theorem itself, but after Steve's comment, it looks more promising. But of course, it may also be that from my point of view, one is more interested in this analog rather than in the original property.
To get a version of
We're hearing yourself. We'll wait for the delay, and then we'll see if Peter replies.
theorem itself.
We're waiting for the delay, and then we'll hear if Peter has a follow-up.
It looks more promising. Of course, it may also be that from my point of view, one is more interested in this analog rather than in the original.
Okay?
Okay, thank you. Thank you. I don't have a...
Okay, goodbye.
Yeah, we're done here.